But you're all set up for the project. Yeah, just make sure that's all. So why are you setting up tonight?
Yeah, I think that unfortunately that happened. But it just happened. Yeah. How do people go back?
Check. Audio check.
Right. Welcome everyone back to the final keynote session of the conference. We have Professor Saurabh Bagchi, who is a professor in the School of Electrical and Computer Engineering and the Department of Computer Science at Purdue. He's also the CTO of a cloud computing startup called Keybyte. His research interests are in dependable computing and distributed systems. He has many awards, 13, I think, Best Paper Awards or Runner-Up Awards, Test of Time Award, and many other accolades. So in the interest of time, I will hand the floor over to Saurabh to get started as quickly as possible. Saurabh, over to you.
All right. Is the audio coming through? Thank you. Good morning. Thank you, Monisha, for the introduction. My name is Saurabh Bagchi, and I'm going to talk about two topics which have been in the news a lot. One is dependability and one is data analytics. And I will share with you our journey through seeing how dependability and data analytics can actually come together to build usable large-scale systems. And I represent work done as part of a center that I lead, CRISP, and an institute that I lead called A2I2 at Purdue. So to get you geographically situated, Purdue University is here. It's in the state of Indiana. And the closest geographical reference many people relate to is that it's about 2.5 hours from Chicago. This is founded all the way back in 1869 and is a largish US university with 50,000 students. And this is what it looks like on a bright sunny day. My lab is right around here. So I have about 20 researchers working busily while I travel the world and give talks at places like this. This is what it looks like on a bright sunny day. Today, it's not a bright sunny day. Today, it looks more like this. So if you ever want to do sledding when it's minus some temperature in Fahrenheit, then you're most welcome to come by. As I said, I'm representing work that is done in our research group, but also more broadly within our center called CRISP, which is about 35 faculty members encompassing computer science, electrical and computer engineering, and many, many departments in the College of Engineering. And as of 2 years back, we had an institute founded here called the Army's Assured Autonomy Innovation Institute, which looks at machine learning and security. And some of my talk here is going to draw upon things that we have built as part of this institute. So in my talk, I have some high-level context, high-level perspective, and then for those diehards who really want to get into some details, I also have some details about which represent work done at several of our, work that has appeared at several of our papers. So I'm going to start off with a high-level view of what dependability across the computer system stack means. And when I talk about dependability, let's get some terminology basics out of the way first. So what dependability means is that a computing system would be able to provide the expected functionality, the correct functionality, within reasonable time bounds. And this it is able to provide despite the occurrence of various kinds of faults. So it's going to be able to provide dependability despite the occurrence of natural errors, which are errors in hardware and software that are not because of malicious intent, but are naturally occurring. It would be able to provide this functionality despite the occurrence of security errors, and these security errors may arise either from inside the system or from outside your system. So these could be insider attacks or these could be external attacks. And something that has emerged over the last maybe 5-ish years is these systems must also be able to operate dependably despite unintended interactions between the human users and the computing system. So this was not an important topic of discussion before, but has become one over the last 5+ years. So here is a very simplistic linear view of, almost linear view of how dependability is achieved. So in order to achieve dependability, you go through these various stages. So you start off by trying to prevent errors in the first place. So this is where we teach our students, our colleagues, how do you develop hardware and software which are intrinsically dependable. So use the best software development methodologies, use the best software verification methodologies, use the best software testing methodologies in order to prevent the insertion of faults in the first place. But in cases when that is not going to be possible, you want to be able to detect when there are errors which arise during the runtime operation of your system. So when errors arise during the runtime operation of your system, you want to be able to quickly detect these errors. Then you want to be able to diagnose these errors, meaning you want to perform the root cause analysis to see which is the component which is failing so that you can isolate it. In some cases, you're able to contain this error. So think of a large-scale distributed system with many, many software components. You don't want it to be like a house of cards where one card falls down and the entire system falls down. You want some level of containment whereby you're able to contain this error to one or a few offending components. And in a small subset of the cases, you are able to do repair, whereby you're able to automatically recover your system to a pristine state. Maybe it's a degraded state, so you don't have to stop the world, but you can continue operating despite the occurrence of these errors. Okay, so that's the basic way in which dependability is achieved and the kinds of fault models that we have to deal with. So now, if you think about the way this field has emerged, there are two emerging trends that have become quite clear over the last 5 to 8 years. So the first trend is that before, the execution environments were all relatively homogeneous. So you were having hardware which looked exactly the same on all the nodes. You had software that was either developed in-house or you as the owner of the system had complete visibility into the software and had complete controllability of the software. You understood the software at a deep level. You could make changes to the software as you wished. So this was days 5 to 8 years back. Now increasingly software systems fall in this bracket whereby they're made of third-party software components. So you have not developed them in-house. You don't understand them fully. In some cases, they're black box to you, so you cannot even control them because you don't know the internals of these software components. And they run on heterogeneous nodes, meaning you can have one node which is an ARM processor, another node which is an Intel processor, and another one which is an Intel processor equipped with an accelerator. So you've got to be developing software which can run on these heterogeneous nodes. And importantly, for this discussion, you've got to be developing such software which can operate in a dependable manner. So that's the first trend. The second trend is that these dependability solutions used to be static and rule-based, which would say things like, so this is an example of a simplistic example of a static rule-based system. You have the simple function which is supposed to calculate the square root of a value. You check that the value is greater than 0, and then you assert this. So the result must be, if you squared that result, you should get this original. No matter what value of x it is, no matter if it's 100 degrees outside or if it's 0 degrees outside, this assertion should always hold true. So this is an example of a static rule-based system. Another example of a static rule-based system, this is used in several data centers of one of our collaborators, cloud vendor, is this. So you're monitoring various metrics on your nodes. You find that if your CPU load is greater than that threshold, or your memory occupancy is greater than that threshold, there is a problem of an imminent performance failure, and therefore you're going to move your virtual machine from this physical node to another physical node. So this kind of a rule is being used at all times under all contexts. Okay? Now, in the brave new world, these kinds of static rule-based systems are giving way to systems where you learn these rules, and these rules don't apply at all times. These rules are based on the context. So here is an example from our NeurIPS paper. This is trying to detect some security failures in sensor networks. Okay? So what you have here in the blue is the benign data. So your sensors are giving you some data. And some of these sensors may get compromised or they may fail. So your objective is to try to tell when this data is gone anomalous. So a strategic adversary, what she would do is she would inject a data which would fall within the range of the benign data. So if your rule said, as long as your data lies between this minimum and this maximum, then I'm good, then that kind of a rule can be easily bypassed. So what is the solution that we came up with? Instead of looking at individual data points, you look at the distribution of the data over a certain length of time, over a certain geography. So this blue one denotes the benign distribution. And then when you're getting data from what could be an anomalous node, you find that the distribution looks like this red one. And it's obvious here even visually that the red distribution is very different from the blue distribution, even though an individual data point in this distribution may well have passed your rule-based check. So this is another emerging trend that has really become quite widespread in the way we develop dependable systems. No more static rule-based systems, but dynamic systems where the rules are learned based on the data, and these rules may change based on the context. So while we'll have about 8 to 10 minutes at the end for Q&A, if anybody has a burning thought, question, feel free to raise your hand and shout it out even as I'm going along. Please.
There could be cases where we consider data from multiple sources or different vendors, where that adversarial may be one of the possibilities. So how do you take care of that?
So are you asking if I'm able to tell if it is naturally erroneous or adversarial?
So maybe 3-4 options are there, and the natural one could be option 1, and maybe there's no direct separation between an adversarial.
I see. So if the distribution of adversarial data looks very similar to the distribution of benign data, then it's not possible to tell them apart. But in most cases, adversarial data is meant to look very different because it is trying to throw off a model. So it looks very different from a benign data. All right, so I'll plow along and I'll again give you some chance to have a discussion or throw out your thoughts. So now I frame this problem of dependability across the system stack in terms of 3 questions. So the first question is, so here is a somewhat simplified, abstracted view of the system stack. You start off with low-end embedded devices. These are your embedded devices made by the Honeywells of the world, which are embedded in our physical spaces. Going up wearable and mobile devices, going up to clusters of edge devices, then you're thinking of data center systems at large scale. And finally, at the highest level of abstraction, you're thinking about these autonomous systems, autonomous transportation systems, autonomous financial transaction systems, which are operating mostly autonomously without human input. So when you think about dependability across the system stack, then for each level of the stack, there are 3 kinds of questions that you want to ask. So the first question is, what is the unique problem context that level poses to you? What are the requirements? What are the constraints? So the second one is the requirements. What are the domain-specific requirements that come from that level of the stack? And the third one is, what have been some success stories in applying data analytics in order to build dependable solutions at that level of the stack? And this obviously is going to be a small subset of the latest results that I'm going to preview for you. And in the interest of time, I'm not going to go through all layers of the system stack, but I'm going to pick and choose 2 or 3. So let's look at your mobile and wearable devices. So what does it mean to build dependable systems using mobile and wearable devices? So the problem context has some unique challenges in there. So one unique challenge is that there are new failure modes for these wearables. So the smart watches or the smart glasses that you're wearing will have a very different software patterns than your desktop class, server class software, and even a different software patterns than your mobile devices. So for example, on your server class systems, your software patterns may have much richer human interactions, user interactions. Whereas on these kinds of wearable devices, because of the smaller amount of real estate, the the richness of the user interactions is much, much less. And then another one is that with the proliferation of sensors that are there on these wearable devices, you want to be able to do crowd sensing of information. So suppose you want to find out where the noise level is lower around this place. Your answer may be there's no place where the noise level is low, but you want to be able to gather this information, and because of microphones which are there on our wearables, on our phones, you could gather this in a crowd-sensed way rather than having to install expensive fixed mode infrastructure for them. Now, this is the problem context. So now let's look at what are some domain-specific requirements from this problem context. So the first one is that these kinds of devices are inherently unreliable. Your mobile device may run out of battery, your mobile device may have a software failure, which may crash it, or which your sensor that is there on these devices are fairly low cost. Therefore, these sensors may act erroneously. So you still want to build reliable systems out of these unreliable components. So this is a broad philosophy that the community is pursuing, is how do you build reliable systems out of inherently unreliable components? And you use the fact that there are many, many of these. So there is wisdom of the crowd. So there is comfort in the fact that there are many, many of these devices, and hopefully not all of them are going to fail simultaneously in the same way. The second requirement that comes from building these systems is that they have to be relatively unobtrusive to the human users. You cannot expect a human user to interact with these on a frequent basis, pressing this button, swiping left and right in order to achieve the desired functionality. Now, there have been, over the last 3-4 years, there have been some promising developments, some even foundational developments in here. So one class of work has shown how do you infer human intent through these kinds of interactions. The second work, which is really emerging, evolving still, is because these devices are on us, they are with us in all kinds of spaces, including private spaces. How do you make sure that this inference does not leak private data? And the third one is what I alluded to earlier, is because you're doing crowd sensing and individual sensor data may be unreliable, maybe even maliciously corrupted. How do you build a reliable map of the physical world around you from this kind of unreliable crowd sense data? Moving up in the software stack, if you look at clusters of edge devices, so this is somewhere between your mobile wearables and the data center, and this has been a fairly growing area of research and commercial activity in developing edge-based systems. So the problem context here is that edge capacity is not fully elastic, unlike in data centers. What does that mean? That means, let's say your demand on your edge system becomes 2x. You cannot suddenly spawn up 2x number of VMs on these edge systems. There just does not exist that level of elasticity. The geographic scale is much larger. You can have an edge device here, you can have an edge device in Hyderabad, and these edge systems in somewhat of a futuristic scenario are supposed to be able to work together across these large geographical scales. And then the client devices which are accessing these edge devices are extremely heterogeneous. So the requirements that come from building dependable systems with these edge systems, edge devices, is that you got to have very low latency. So one of the big driving factors why people are looking at edge-based systems is that the latency between your user client device and the edge device is expected to be of the order of 10 milliseconds. And just round figures, if you're thinking of your latency from your client device to your data center, it's of the order of 100 milliseconds. So there is going to be growing development of applications which require that 10 millisecond or even lower latencies. Therefore, as you're building dependable systems, you've got to keep that latency envelope in mind and cannot exceed that latency envelope. And another growing problem statement here is that these edge devices that we're talking about, some of these are going to be provisioned by the cloud vendors. There already are edge offerings from all the top cloud vendors, Amazons, Microsofts, and Googles of the world, but they're going to coexist with unmanaged edge devices. So what do I mean by unmanaged edge devices? Unmanaged edge devices are those that you and I carry with us, maybe a tablet that we have which is not being utilized a lot. So for example, on Purdue's campus, you have many, many computers in the classrooms. When the class is not going on, there is spare excess capacity in there. So if you want to run some demanding application, you can offload this to a nearby computer or a tablet with excess capacity. So that's an unmanaged edge devices. So there are 3 important developments that have happened with this. The first one is, how can I take these machine learning algorithms, streaming machine learning algorithms that need to operate on streaming data, and squeeze them down so that they can operate on these kinds of edge devices. This is an extremely active area of research, so much so that we are beginning to see the tail off in the innovation in here. The second one is that I can think of my systems as 3 tiers. You have the user or client devices, your mobile devices, your wearables. The second tier are these edge devices. And the third tier is your traditional cloud. So if you're going to build an application, can you build an application that can flexibly flit between any of these 3 layers? Maybe one part of the application can execute on the client device, one part on the edge, one part on the cloud. And currently, there is no way to achieve this. There is no software development methodology, no software pattern that can achieve this. And this is important because the application requirements may change, the networking availability may change, and therefore it's important for you to be able to reliably offload, go back and forth between these layers. And the third one is, with the security flavor, is now you want to be able to do the streaming inference, but some parts of your data stream are strategically corrupted. So when some parts of your data stream are strategically corrupted, can you still make reliable inference? So these are three broad research directions which the community has been pursuing. One of them is relatively mature and the other 2 are evolving. I'll speed up and go to the highest level of the stack here, the autonomous systems. And here, what you're looking at, the problem context is, we have seen machine learning take over our world by storm and give us many, many, many wins. Now, what happens when you take your standard machine learning algorithms, which are well-baked, runs well on your data center clusters, and you now want to have them run on these heterogeneous platforms, okay? And it turns out that it's just notoriously difficult to take your standard machine learning stack and port it over so that it can run on distributed heterogeneous platforms. There are many, many sources of error that crop up. For example, if you don't have a correct matching of the input rate and the output rate that this platform can support, your algorithm just crashes and burns. The second problem context that comes in here is that by nature, these are less managed, less protected systems, and therefore you've got to be able to deal with strategically injected errors into the data streams. And the third one is that you're going to have not a single model, but you're going to have an ensemble of models matching the resource availability on these different platforms. So how do you pull together an ensemble of machine learning models and build something cohesive, something usable together? The requirements that come out of this is many of your machine learning models are going to be black box, and you still have to make appropriate inferences about, is this reliable, is this secure out of these black box models? The data sources are going to be noisy, sometimes strategically, maliciously corrupted, and then the execution platforms are going to be unreliable. So this is a strong departure from the world that we know of today, where your machine learning algorithm is running on your data center. Every single machine is well provisioned. It's going to be there today, tomorrow, and a month after. In this kind of a system, these execution platforms may come and go, and sometimes in a somewhat unpredictable manner. So there are 3, again, areas here where there have been some successes in applying data analytics to building dependable systems. The first one is detecting adversarial samples. A lot of top work showing up at the top security conferences, as well as some in the machine learning community. How do you do situational awareness in a distributed manner? How do you figure out which of these nodes are likely compromised and which others you can still rely on? And you want to do this in a distributed manner. There isn't a single central platform where all of this can run. And then how do you protect against model and data poisoning attacks? Again, a lot of good work is showing up at the top security conferences in here. All right, so I'll finish off this high-level view of the world by looking at one other piece of this puzzle, which is how do you build dependable systems? So abstracting it out, you can think of dependable systems being built using in two phases. One is dependability by design, whereby you design your protocol so that it's dependable from the ground up. So you figure out what are all the different ways in which your components may fail, in which different component interactions may fail, and you create preventive mechanisms so that these kinds of failures don't show up at runtime. However, despite your best intentions, you are going to have dependability outages at runtime, where some interaction that you did not anticipate is going to show up and is going to bring down one component, multiple components, maybe your overall system. So then what you do is, in this learning-based regime, you learn of these interactions. You learn of these kinds of failure patterns. And once you learn of these failure patterns, you take them back and you make them into dependability by design principles, so that the next iteration of your system, these are done by design, rather than you having to learn in a much more painful, much more expensive way of the dependability by reaction. Dependability by reaction, almost by definition, is going to set you back longer. It's going to be more expensive in terms of how long it takes for you to recover. Now, what our community is doing is this loop from dependability by reaction to dependability by design is becoming faster and faster and faster as we build better ways of learning all of these patterns. How do components interact? How do components fail together? How do adversarial inputs come in and break our system? As we learn this, and in an autonomous manner, we are able to make this transition better and better and better. Now, I'll give you one simple example of this from our own work. So this is work that appeared at Security and Privacy last year, and it was featured in a Wall Street Journal article in October of last year, is if I have these large-scale critical infrastructures and I want to protect them, okay? So think about your transportation infrastructure or energy infrastructure, and I want to protect them. Now, I cannot wave a magic wand and say I'm going to protect every single component in my large-scale critical infrastructure to the same level. Therefore, what I have to do is I have to make strategic decisions about which components do I protect. How do I make these strategic decisions? So we've shown this methodology whereby you can conceive of your system as through a graph. This is called an attack graph. What that means is if you can get to node 1, you can use that privilege in order to get to node 2 and so on till you get to the crown jewel. So in order to protect this kind of a system, I have to make security investments in these various nodes. And we've come up with an algorithm which, under a fairly wide set of assumptions, is able to say, I learn the min-cut edge set in the attack graph. I invest in the security protections on all the edges in the min-cut set. And I learn what is the appropriate level of security investment on each edge. So this we learn, and then we can now, during design time, we can say, and this is something that's being now used by a federal agency in order to come up with cyber insurance. How much do you need to invest in protecting various components in your infrastructure? And that's why it got picked up by the Wall Street Journal. So this is an example whereby initially you learn this by reaction, but then you can bake this into the way you design and run your large-scale critical infrastructure. So that's the high-level approaches that I've covered with you. And I have run through about half of my time, I see. So let me pause here for a little bit and see if there are any questions, thoughts you'd want to shout out.
Thank you. So this is Subrat. So I wanted to ask about the last slide where you paused earlier. So in that, like you said that instead of learning the clear boundary, you are learning the distribution of the dependables. I mean, all those benign data. So my question is that if somehow the adversary kind of shift the benign distribution and then attacks the system in adversarial manner, so will that be possible?
Yeah. So you are referring to what is termed in the security community as a white box or an adversarial attacker. So an adversarial or a white box attacker is one who knows your defense mechanism, who knows your defense algorithm. It may even know any kind of a hyperparameter value you have in your defense algorithm. And your defense algorithm still has to be resilient, resistance to attacks. So initially it may think that this is a fool's errand. There is no way you can achieve this. But the community has developed a set of fairly well-disciplined methods now whereby we are able to tolerate adversarial attackers and white box attackers. And the general principle is as follows. So in order to bypass the defense mechanism, the attack has to be adaptive and has to change. And the attack has to adapt and change in a manner that this attack becomes toothless. This attack becomes one which does not damage your system. So that's really the high-level view of how these defenses are created. And we've adopted that kind of a methodology as well. Okay. Any other question?
Hi,
There's a question there, right behind you.
This is Partha from Nokia. When looking at the 3GPP delegate, you have clearly mentioned that many models are black box as a requirement, right, for autonomous system. So this is the same thing we are saying in 3GPP as well. So what are the actual well-known solutions? Basically, like what the thing is, I understand the models are the values, and today it's a black box. What are the well-known solutions in the? It will be good to hear.
Yeah. So if I understand your question, let me restate it to make sure I understood it. You're saying we have got to live with black box machine learning models. How do I still build dependable solutions using black box machine learning models? So broadly, the community has come up with two approaches. One approach is, even though the model itself is black box, I get an understanding of the input-output patterns. If I feed it this input, I expect this output. So if it's adversarial, then this input-output pattern that has been learned will be violated. The second approach that the community has come up with comes often under a broad umbrella of explainable AI or interpretable AI, whereby I take these machine learning models, which are black box, and I try to approximate parts of them using easier to understand models. So for example, I can take a rather deep neural network, and parts of it I can approximate using piecewise linear models. So I have to give up something in the accuracy, but what I gain is a greater level of understanding and sort of a white box or a gray box nature for this. All right, I'll plow along. And I have maybe about 15, 18 minutes. I'll leave some time for Q&A at the end as well. So as I get into the deep parts of this presentation, if you find your attention wandering, you can try out this fun quiz, which has got some computing related stuff, and you'll be able to get to the answers of this. So at the end, I will ask, on an honest honor system, you can tell me who got how many, who got the maximum. Okay. So now I'm going to tell you about how do I auto-configure systems for the cloud. Okay? And this is based on work that has appeared at ATC and DSN. And since then, we've commercialized this in a startup. And of course, as many of you realize, there is a big chasm between your paper that appears even at the top conferences and when you can have somewhat of a usable prototype. And we now have a release of the software for general availability. And I'm going to show a demo of that time permitting. So here is the broad context for this work. So as we are talking about distributed applications, distributed systems, they have many, many configuration parameters. And I want to be able to configure these systems in a manner whereby I can meet certain requirements. These requirements could be for latency properties, could be for throughput properties, these could be for reliability properties. So the fact of life is that these distributed systems applications that we rely on are complex enough and with so many configuration parameters that have pairwise or even n-way dependencies that if you get the parameter of one of them wrong, that can completely sink your latency or your throughput or your reliability. So what the community has come up with increasingly is auto-tuners, which are able to automatically tune these kinds of configuration parameters for these distributed applications. Now, the problem becomes one level more difficult when you're talking about stateful distributed applications. So what do I mean by stateful distributed applications? Databases are the quintessential example of a stateful distributed application, which store large amounts of state within them. Now, why are stateful distributed applications so hard to configure? Because you don't have the ability to shut it down and start it back up from a clean slate. Because by definition, they carry with them a lot of state. So as you are migrating these applications from one node to another, you've always got to keep in mind the amount of state that they have, and you've got to take into account the migration costs of the state. And as a result, it has been found that a fairly large chunk of the time of database administrators or cloud administrators are spent in configuring these kinds of stateful distributed applications. So the challenges are, even if you take a leading NoSQL database called Cassandra, it has of the order of 50 performance tuning parameters, and a much simpler one called Redis has 46 such parameters. Now, the workloads can change quite frequently, meaning that if you set up your system just right on day one, your workload patterns may change. What was originally a very read-heavy workload may now become more balanced between read and write. Or what was originally very large reads may become smaller reads. So it turns out that even changes in the workload patterns will have to be accompanied by changes in the configuration parameters of your distributed application. So the big open question that we had going back about 3 years was, how can I automatically tune stateful distributed applications under the fact of life that the workload patterns are going to be changing for them? So now another level of twist in this puzzle is when you talk about cloud-based distributed applications. So cloud-based distributed applications reside in the cloud, and the cloud computing environment themselves provide you with a fairly rich space of configurations. So depending upon what kind of virtual machine you choose, you will have different amount of compute resources, memory resources, storage resources, network resources. So AWS, for example, provides you with 400 instance types, and the prices for these instance types vary by a factor of 5,000x. So you're talking about not just your latency, throughput, reliability requirements, but you're talking of these requirements being satisfied under dollar budgets, under certain dollar budgets. And so the big open question is, in the cloud configuration spaces, how do I choose the right configuration so as to meet the right amount of performance normalized by the dollar cost? So the insight that we had going back about 3.5 years, was that it's not enough to configure your stateful distributed application like your database and your cloud separately. You've got to configure them together. Because as an example, the optimal cache size that you would need for Cassandra for a VM type of M4 large is 8x the optimal cache size for a C4 large, which means that when you're configuring your distributed application, you've got to keep in mind the joint optimization with the cloud space. And further, if you think that I'm just going to choose the largest size VM that's possible, then it's obviously not a good solution because you're normalizing by the dollar cost. A larger VM is going to cost you more. So here is a pictorial representation of the variability in the performance by even changing a single parameter. Okay. So depending upon what kind of a cloud configuration I choose, I can have a small or a large variation in the performance. So you can look at the default configuration, which you get right out of the box. You can get the worst configuration, and you can get the best configuration. So the big problem statement is, how can I get closer and closer to this, even when I'm choosing different kinds of virtual machine instances? Okay, so now you may think there is a disconnect between the first part of the talk that I gave about dependability and this part of the problem space. So what does performance tuning have to do with dependability? So if you think about it a little more deeply, when I'm talking about a dependable system, I said that it needs to provide the required functionality within a time bound. And as soon as you bring the time bound into the picture, then you've got to take into account the latency that is achieved by your system. If your elevator stops, but it stops 3 seconds after it's supposed to stop, then you don't care. It needs to stop within that time bound. So this is, of course, an extreme example of a critical hard real-time system, but even for other soft systems, there are requirements for the latency. So I want to be able to meet the latency requirement, otherwise I have, quote unquote, a failure. And this may have a financial impact, or in some cases even a safety impact. So for example, when you're talking about autonomous transportation systems and I want to do reads and writes from our databases, I need to do this within time bounds, otherwise your car is going to crash. And this is a textbook version of failure patterns. So starting with the easiest to detect to the hardest to detect, and the timing errors comes in here. So we talk about timing errors, and that's why the performance tuning is a part of the dependability piece. So I'll cut to the chase quickly. Now, when we talk about this distributed reconfiguration, in order to understand our solution, let me show you this synthetic viewpoint, which is quite representative of reality. So when you have workload 1, you have a certain configuration of Cassandra. Okay? Let's say workload 1 is a read-heavy workload. And under that configuration of Cassandra, I'm getting 70 kiloops per second. So that's the measure of the throughput. Now, the workload is not static, so the workload is changing under you. So the workload changes from workload 1 to workload 2. So if I stick with conf 1, then my throughput goes down to 40 kiloops per second. So now, using the best technique which is out there, I decide that conf 2 is a better configuration for workload 2. So I switch to conf 2. When I switch to conf 2, my throughput goes up somewhat to 60 kiloops per second. But again, the workload is not static. You have no control over the workload. That's what's coming from your customers. So now it changes back to workload 1. And it turns out that conf 2 is really, really bad for workload 1. So the throughput now goes down to a terrible 30 kiloops per second. Okay? So now the question for you is, when it changed from workload 1 to workload 2, should I have switched to conf 2 or should I have stuck with conf 1? In this example, I switched from conf 1 to conf 2. I did see a benefit in here, but then when it came back to workload 1, my throughput really tanked. So what should we do? So that's the right answer. I gave an insufficiently specified question. The answer to that will depend on how long workload 2 lasts. If workload 2 lasts for a long period of time, then it was worthwhile switching from conf 1 to conf 2. If, on the other hand, workload 2 is very transient, then there is actually pain and cost incurred when I switch from one configuration to another configuration. In many of these stateful distributed applications, I cannot do what's called a live upgrade. I have to change the configuration, I have to shut it down, I have to migrate the state, which could be gigs of data, and then I have to change the configuration and bring it back up. So there is cost involved in switching from one configuration to another. And I don't want to incur that if my workload 2 is going to be very, very transient. Clear? If you understand this, then all the 2 years worth of work by my grad students, that's details. This is the concept behind it. And my grad students would shudder if I'm compressing their 2 years worth of work in a 5-minute detail. But this is the key. So now, as soon as you understand this is another way of looking at it. My black curve is the throughput. So the throughput increases, and this dotted curve is the gain over the default. The default is I don't change anything. I download my distributed application, I use whatever configuration comes out of the box. So I want to be in the part of this dotted curve which is above 0. And it's above 0 only if this workload lasts for more than like 330 seconds. So I want to be able to predict how long my workload change will last. I want to be able to predict what is the cost of making this transition. And I want to be able to predict what is going to be the benefit of making the transition in terms of throughput or latency or what have you. And those are the 3 pillars which let you figure out what should be the best configuration space for your stateful distributed application. Now, another very important piece of this puzzle is I want to figure out the joint dependencies between the application and the cloud. So till we came in and did this work, there was no solution out there which would take this kind of cost-benefit analysis into account. And you have to consider the fact that when you're making this switch, your data becomes transiently unavailable. And unavailability is a no-no when you're building a dependable system. So that should figure into the cost that you incur when you are talking about these kinds of systems. All right. So that's our solution, Optimus Cloud. And then this is your traditional bragging chart that you have in your papers, which shows you have a tick for all of them and no other prior work has a tick for all of them. And I don't have a time for the demo, but I'm going to share the demo URL with you to show that this is not just vaporware which sits in papers, but now we have a prototype implementation of that, which is now available for general release. Let me skip to a later part of the presentation. So the takeaway from this is sort of twofold, two high-level takeaways that you can use as you're designing these kinds of adaptable cloud-based systems. The first takeaway is that you've got to take into account the dependencies that exist between your application and the cloud VM instance type or any other cloud configuration space. The second one, where we did not go into the details in here, is you've got to be able to operate in a heterogeneous world, which means that some nodes of your stateful application are going to run on an M4 VM, some are going to run on a C4 VM, and some are going to run on an I4 VM. So this kind of heterogeneity is important in order to achieve your latency goals. And finally, you've got to think about your performance metric normalized by the dollar cost. And when you're talking about these performance metrics for certain performance critical or certain critical applications, you've got to think about not just your median, not just your P50. You've got to think about your P95 or your P99. So what we found is that systems which operate quite well in the P50 regime completely fall apart when you're looking at a P95 or a P99 latency. So that's another insight from this. Sort of a high-level view of this world is, why is this notion of dependability and data analytics coming together? So there are fairly inexorable market forces that are also driving this because of growing data volumes, infrastructure complexity, and the scarcity of skilled security professionals, whereby these kinds of learning mechanisms in order to learn what are the right dependability attributes, right dependability configuration, that's become quite important. In security analytics, there are these four foundational technologies that come into play: network traffic analysis, endpoint detection, SIEMs, which are fairly well-established, mature software stacks, and then user behavior analytics, which is currently being developed. So these all feed into security analytics. And taking a business view of the world, if you look at big data analytics, it's having a compounded annual growth rate of 13%, fairly large market size already, but expected to grow over the next 8 years at a 13% rate. Cybersecurity, again, a reasonable 9% CAGR. And if you put these two together, the security analytics world, the best estimates have it growing at an astounding 24% CAGR to lead to a fairly large market size. So these kinds of market forces are playing into the research community, which is driving the adoption of data analytics in security, in reliability. All right, so I'm going to spend maybe 5 minutes telling you about another form of cloud computing where auto configuration is also very important. This is called serverless, and this is very recent work that's come out of our lab. And in serverless, what we have is, it's an attractive model of pay as you go. You don't need to rent VM instances by the hour or by the minute. You can pay for exactly the kinds of resources that you need. And these are supposed to give you very low latency output. So a picture of the road from outside here comes in. You classify it quickly to determine if there is an accident or not. And then you take some physical action based on it. And you want this to happen fairly quickly. So here is an example of an application written as a serverless chain or a serverless DAG. This application, you would split the video into multiple chunks first. Then you would extract a representative chunk from there. You would classify it saying it's a benign condition or an accident condition, and then you would exit. So if you go back to serverless as it existed, as it started up, it looked at creating individual functions which would run very quickly and you'd be done. But now increasingly we want to build serverless applications which are more complex, which have this notion of a DAG in them. And this issue of how do I configure these kinds of serverless applications in order to meet low latency and low dollar cost has also become important and is currently somewhat of an unsolved problem. So we have a paper in OSDI last year and the best paper in Sigmetrics last year, which was held in IIT Bombay, but that's just scratching the surface of this. And this problem space is become quite important. The serverless world has some somewhat esoteric problem context to it. For example, the different functions in a serverless DAG cannot directly or a point-to-point communicate among them. They have to communicate through an external storage layer. And if you have parallel invocations of multiple functions in the same stage, if you have skew in those invocations, like classify 1 has a short execution time, classify 2 has a long execution time, then it'll be fairly obvious to you thinking about it as this may really mess up your end-to-end execution latency. So how do I configure my individual functions in order to achieve the right amount of latency and bounded by the dollar cost? I see I'm 5 minutes left in my time, so I'm going to skip to the end of this. All right, so the takeaway from this line of work is that in order to build serverless applications which have complexity among them, you have to do certain optimizations, like you may have to fuse multiple functions in one, or you may have to bundle parallel invocations of these serverless functions. And these details, of course, you won't get from this talk, but our OSDI and Sigmetrics papers provide those details. And our work provides the best ways in which you can do these fusions and optimizations, fusion and bundling. And an important thing for the community is that we have partnered with Microsoft Azure in order to release open source traces of serverless DAGs for the first time running on the Azure platform. So the takeaways and the open problems. So if you think about, so what is the broad thesis of this line of work? Is you want to use learning in order to learn dependability solutions from the data, and you want to very quickly move from dependability by reaction to dependability by design. Okay? That's going to allow you to achieve dependable solutions under minimized dollar cost, under minimized latency cost, under highest throughput. And you have to be able to refresh these machine learning models when your workloads change. You have to make updates in an incremental manner. You cannot stop the world and say, I'm going to throw out my previous model, I'm going to learn from afresh, and then I'm going to deploy it. So online learning is very, very important in here. And how do I leverage the natural labeling of data that already comes in from my systems? I know this is anomalous, I know this is benign because of some other out-of-band mechanisms. And this is how do I support complex machine learning workloads, not just individual functions, but DAGs and maybe even more complex graphs, more complex than DAGs, and where there are dependencies across multiple user requests that come in. So this is an open issue in the community. And taking a really step back and a 30,000 feet view of the world, if you're thinking of data analytics for building dependable systems, then obviously it's not a panacea, but there are few aspects to take away. It can help in some cases. It can help when the model can be approximated, can be made somewhat simple so I can understand it, interpret it. And whatever time I spend in inferencing or searching for the optimal model must be taken into account in the overhead of my system. White box is often a desired element, though not always achievable. And then the model must be parameterizable, must be adaptable to the dynamic system conditions. So this work is done in collaboration with large numbers of my corporate collaborators as well as academic collaborators. And I thank them all, including many of the students who've been responsible for this kind of work. Thank you, and happy to take questions and comments.
Thank you very much. We do have a tea break, but I think we have time for some questions.
Hello. Yeah, so in one of the slides, you mentioned about over-provisioning and the performance degradation. So those two are different factors, as we understand, right? So performance is like we are serving the user request, and provisioning the resources is the cost factor, what the operator invests in terms of VMs or the CPU or the RAM. So why do you say that they may not perform better? Like those two are independent factors, right? As we understand.
Yeah. So this is a nuanced question, and we'd already take this into account in our work. Is if you look at metrics, you can look at it from a user standpoint or a consumer standpoint, and you can look at some metrics from a provider standpoint. An example of a metric from a user standpoint is the raw latency I get for my user request. One from a provider standpoint is the utilization of my resources. Yeah. So we also use some metrics which are the latency or performance factors normalized by the dollar cost, because if it's going to cost more to the provider to provision a particular resource, that cost is going to be passed on to the end user, and therefore an M4.large costs more than an M4.mini VM instance. So that's why these performance measures normalized by the dollar cost is often what you want to optimize.
But at end of the day, it is like user satisfaction, right? When we talk about performance, the other one is like the SLA violation, like we are not keeping up to the mark in terms of satisfying the user. Right. But over provisioning, I'm not still getting like why should it really bother in terms of performance?
Well, because the over provisioning costs the provider something, and the provider passes on that dollar cost to the end user, whether immediately or in the longer run. And therefore, that dollar cost must figure into the optimization criteria that you have. But in addition, in the optimization criteria, you also say, I'll do all of this subject to my SLA violations being no more than 5%.
Okay. Thank you.
Other questions?
Thanks, Saurabh, for really interesting thought. So I'm thinking of, like, from a telecom background, reliability is... So the problem of distributed stateful applications is solved, right? So now we have, and we run now on virtual machines. That's also being done. So I was still, maybe I'm missing something. I'm still trying to capture what, what's the hard part here?
So there are two hard parts abstracting out. Okay, one hard part is I want to provision my application and my cloud resource together. And because of dependencies that exist among them, it's a combinatorially hard problem. So I cannot just enumerate all possible configurations of my application and all possible VM instance types and do a cross product of them. So you have to do something smart in order to navigate this large configuration space. So that's problem number one. Problem number two is that the future is uncertain. So while I know what my workload pattern, what my load is now, I have to do this provisioning also in anticipation of how things are going to change, because of this important insight that reconfiguration is costly. It may lead to downtime. And therefore, I have to predict with enough accuracy. It doesn't have to be fully accurate, but with enough accuracy what the future is going to look like so that I can do this predictive provisioning, predictive configuration. So those are the two hard problems.
Perhaps you already answered the question, but I'll ask it again. The VM configuration and workload matching problem, at first sight appears to be a control problem. It's formulated like a classical control problem. So what is different here which will not permit that to happen? Is it the configuration time that's the difficulty here? Or what's the difficulty in applying some standard techniques to this?
So I won't pretend to be a deep control theorist by any stretch, but when I talk to my control theory colleagues, they say that you have to look outside of our realm for this solution. And they bring up two characteristics why they say that. One characteristic is that there is enough, so this is sort of a stock answer to whenever we go to machine learning, is that my problem space is very high dimensional. So it does not admit of nice closed form solutions or even numerical solutions. So I've got to throw somewhat of a higher dimensional model set. So that's problem number one. Problem number two is that there is enough uncertainty in the picture that it's hard to use a traditional or even a recent control theory solution to this. And what do I mean by that? So if I take these 5 cluster of 10 nodes, and I want to predict what is going to be the throughput for this workload type, it turns out that this problem, simplistic at its face, is very hard to do because of the way these distributed applications are configured. It depends upon factors like if I have a machine instance type of M4 in here and I4 in here, if I just switch them in a ring topology, the throughput is going to change for various factors in the way Cassandra is architected or Redis is architected, which is not germane to this discussion. But these bring in what is non-determinism to a system designer. And that is, again, hard to admit of a control theory solution.
I think we have time for one more question.
Hi, Professor. Thanks for the very interesting talk. I'm Venkatachalam from Ericsson. My question is about, you mentioned about the workload, how much frequency it is. Based on that, you will take the reconfiguration. What would be the percentage of new type of workloads that would come in? Because only if we know what is the frequency of workloads and the type of workloads, then we can predict that and make that change. If there are certain considerable percentage of workloads that are coming in with a new pattern, then we need to make a decision. Otherwise, it would be too late.
Yeah. So in our paper, we do a detailed characterization of this. Depending upon how predictable your workload is or not, a solution in this space is going to perform well or will have to be more sophisticated. So an example at one end of the curve is if you look at HPC clusters that are run at these big DOE national labs, they have a fairly good understanding of the workload patterns. And their applications sit in the queue for extended periods of time of the order of tens of minutes. So while your workload request is sitting in the queue, you can analyze it in order to derive properties. So this is one part toward the end of a spectrum where things are more deterministic. The other is this wild, wild world of web applications where workload patterns can change in a very unpredictable manner. And what do you mean by the same workload or different workload? Workloads have so many parameters to them that it's a countably infinite space. So their workloads do change very, very frequently and in unpredictable manner.
Hi, Saurabh, a great talk. Thanks. A quick question, just curious. With the edge evolving so rapidly and exponentially, right? And we are seeing the benefits of edge. How do you see this approach and your paradigm change as edge becomes more predominant and critical?
Yeah, so we have a large edge computing deployment at Purdue spread over a very large farm and as well as a manufacturing facility. So there are two wrinkles to our simple story in here that the edge provides. One is that the network availability is very variable. Even in something as well provisioned as a manufacturing floor, we find that when you have a big steel part being moved in here, the bandwidth from the sensor device to the edge suddenly drops. Okay? So you have to be able to deal with these kinds of unpredictable, unknowable disruptions. That's one. The second one is what I alluded to when I was talking about edge in that system stack, is that in edge, you do not have the level of elasticity that you have in the cloud. So if my load suddenly jumps by 10x, if I were running it in a data center, no problem. I'm just going to spin up 10x more VMs. I cannot do that on an edge. So there, what I have to rely on is being able to offload quickly from the edge to the cloud. So those are the two high-level ways in which this is different.
I think the problem that you just mentioned is you use Ashu's solution with MIMO arrays to detect when this thing is moving, and you know exactly when your bandwidth is going to drop.
Yeah, I mean, that's the benefit of a conference like this. Communications people get to talk to computing people like me. Yeah.
So let's thank Professor Bagchi for an excellent talk. And we have a little gift for you.
Thank you.
Thank you. And before we leave, there are demos and exhibits downstairs, posters by the poolside, and please come to the conference banquet at 7:30. And there's a panel session before.